At 40,000 feet above Earth, a passenger airplane is already flying near the edge of the atmosphere. The air is thin, the temperature is around minus 50 degrees Celsius, and every part of the aircraft, from the engines to the wings, is operating in an environment where physics becomes much less forgiving. But here's the surprising part. A Boeing 787 Dreamliner can be certified to operate at around 43,000 feet. So why don't airlines simply climb higher? Why not fly at 50,000 feet or even 70,000 feet like some military aircraft? The answer is not because passenger planes are too weak, and it is not because there is a secret international rule stopping them. The International Civil Aviation Organization, or ICAO, creates global aviation standards. But there is no universal ICAO rule that says passenger aircraft cannot fly above 40,000 feet. The real reason is a battle between engineering, efficiency, and physics. At extreme altitude, the engines produce less thrust. The wings generate less lift. The aircraft's safety margins become smaller, and the structure faces greater challenges. So the real question is not, how high can an airplane go? The real question is, where does an airplane perform at its best? And for modern passenger aircraft, that point is usually around 35,000 to 40,000 feet. The altitude where modern airliners fly was not chosen randomly. It took decades of engineering development to discover. Early passenger aircraft in the 1920s and 1930s flew much lower than today's jets. Their piston engines produced less power, and most aircraft had unpressurized cabins, limiting how high they could safely operate. The biggest transformation came with the jet age. The de Havilland Comet became the world's first commercial jet airliner. But aircraft like the Boeing 707, introduced in the late 1950s, helped make jet travel practical around the world. Jet engines allowed airlines to fly higher, faster, and more efficiently than ever before. But engineers did not simply choose an altitude and hope the airplane would be safe. They discovered these limits through testing, calculations, and thousands of hours of engineering work. The first challenge at high altitude is something every jet engine depends on. A modern turbofan engine is not just a machine that burns fuel. It is a giant air processing system. Aircraft like the Boeing 787 use either the General Electric GNX or Rolls-Royce Trent 1000 engines depending on the aircraft version. These engines pull huge amounts of air through the front fan. That air is compressed, mixed with fuel, ignited, and accelerated backward to create thrust. Unlike a rocket, a jet engine does not carry its own oxygen. It depends on the atmosphere around it. Think of a jet engine like a giant vacuum cleaner. At sea level, it can pull in a massive amount of air. But at 40,000 feet, there are far fewer air molecules available. The compressor can squeeze the air, but it cannot create more air. Eventually, the engine reaches a point where the thin atmosphere limits how much thrust it can produce. The wings face the same problem. Aircraft fly because wings create lift by interacting with moving air, but thinner air means fewer molecules flowing over the wing. To maintain lift, the aircraft must fly faster through the air. So climbing higher creates a trade-off. Higher altitude reduces drag, but it also reduces engine performance and aerodynamic capability. Another major challenge is something pilots call Coffin Corner. Every aircraft operates inside a safe flight envelope. Fly too slowly and the wings cannot create enough lift. The aircraft approaches a stall. Fly too fast, and the aircraft approaches its maximum Mach limit, where aerodynamic forces and compressibility effects become dangerous. At normal cruising altitude, there is a comfortable gap between these two limits. But as an aircraft climbs higher, that gap becomes smaller. The stall boundary and the high-speed limit move closer together. The airplane does not suddenly become uncontrollable, but the safety margin becomes much narrower. Small changes caused by turbulence, temperature, aircraft weight, or speed adjustments become more important. That is why pilots do not simply climb until reaching the aircraft's maximum altitude. The highest altitude an airplane can reach is not always the best altitude to operate. There is another challenge passengers rarely think about: the environment itself. At cruising altitude, temperatures can drop below minus 50 degrees Celsius. Aircraft systems, electronics, sensors, engines, and materials must continue working reliably in extreme cold. The aircraft is also dealing with extremely low pressure outside the cabin. Engineers must design airplanes that can survive extreme temperatures, pressure differences, and thousands of flight cycles over many years. The Boeing 787, for example, uses advanced carbon fiber composite materials to reduce weight and improve efficiency. But designing an aircraft to fly much higher would require different engineering solutions. A stronger structure could require more material. More material means more weight, And in aviation, extra weight means higher fuel consumption. Once again, engineers must find a balance. So why do airlines usually cruise between 35,000 and 40,000 feet? Because this is where everything works together. Higher altitude reduces aerodynamic drag. The aircraft can cruise efficiently, and fuel consumption can be reduced. But maximum altitude and optimum altitude are not the same thing. Aircraft like the Boeing 787 and Airbus A350 can reach around 43,000 feet. However, airlines usually do not cruise there because the aircraft is no longer operating at its most efficient point. During a flight, the aircraft becomes lighter as fuel is burned. That is why pilots sometimes perform a technique called a step climb. The aircraft starts lower when it is heavy, then gradually climbs higher as fuel is consumed. Airlines also consider the atmosphere itself. High-altitude winds called jet streams can either help or hurt a flight. The best altitude depends on aircraft weight, weather, wind conditions, and fuel efficiency. The goal is not reaching the highest altitude. The goal is finding the most efficient altitude. But this raises another question. If the air becomes so difficult above 40,000 feet, how can fighter jets fly much higher? The answer is simple. They are designed for a completely different mission. A passenger aircraft is built to safely carry hundreds of people across thousands of miles while using as little fuel as possible. A fighter aircraft is built for speed, acceleration, climbing ability, and maneuverability. The F-15 Eagle is commonly listed with a service ceiling around 65,000 feet. The F-16 can operate above 50,000 feet. And the SR-71 Blackbird was designed for extreme altitude reconnaissance missions, operating above 80,000 feet. It achieved this using specialized engines, titanium construction, and a design created specifically for high-speed flight. But these aircraft make huge sacrifices. They do not carry hundreds of passengers. They are not designed for decades of economical airline operation. They solve a completely different engineering problem. There was also one unusual passenger aircraft that flew much higher than today's airliners, the Concorde. The Concorde operated at around 60,000 feet. Why? Because it was designed for supersonic travel. Its slender delta wing and powerful engines allowed it to fly faster than twice the speed of sound and operate at a much higher altitude. But this came with major compromises: high fuel consumption, limited passenger capacity, and expensive operation. The Concorde proved that passenger aircraft could fly higher, but it also proved that higher is not always better. So how do engineers know exactly where an aircraft's limits are? They do not guess. Every new aircraft goes through a detailed certification process. Manufacturers use computer simulations, wind tunnel testing, structural testing, engine testing, and thousands of hours of flight tests. Test pilots gradually expand the aircraft's flight envelope. They study questions like, how does the aircraft perform? At maximum altitude? How much thrust do the engines produce in thin air? How much lift can the wings generate? How does the structure handle pressure changes and aerodynamic forces? Engineers analyze the results, and aviation regulators review the data before approving operating limits. So when you see a passenger aircraft cruising at 35,000 or 40,000 feet, that altitude is not a random choice. It is the result of decades of engineering, testing, and safety analysis. So why don't passenger planes fly at 50,000 or 70,000 feet? Because the highest altitude is not always the best altitude. Flying higher provides advantages: less drag, potentially better efficiency, a smoother ride above weather, but physics creates limits. The engines receive less air. The wings generate less lift. The aerodynamic safety margin becomes smaller, and the aircraft must survive a more extreme environment. Commercial aviation is not about defeating physics. It is about finding the perfect balance with it. The sky does not have one perfect altitude. Every aircraft has a point where physics, engineering, and economics meet. And for modern passenger aircraft, that point is around 40,000 feet above Earth.